We're going to continue our study of vector spaces with the concept of a subspace of a vector space. So a subspace is defined in the following way. First, let's suppose we have a vector space. So let V be a vector space, and W be a subset of V. Then we say that W is a subspace of V if W is also a vector space. So this is a subset that is also a vector space. That's the definition of subspace. So let's maybe look at some examples of this. First, it's handy to have this this theorem which gives us a faster test to determine if something is a subspace. This will be almost the go-to because we saw previously that proving that a vector space is very tedious. This gives us a much faster test to determine whether or not we have a vector space. So this is the subspace test, and the way this works is we say so if V is a vector space, then we've got three things to watch out for. So first up, if W is a subset of V. So this we have to have that every element of W is an element of V. If also W is closed under vector addition, and W is closed under scalar multiplication. So if it is a subset and it is closed under the two vector space properties, then W is a subspace of V. So let's look at an example or two of using this test to determine subspaces. So first up, we saw last time the set of polynomials. So let's let W be the set of polynomials of degree less than or equal to 2. So this is quadratics, linears, and constants. So first up, W is a subset of the set of polynomials. Every polynomial of degree 2 is a polynomial. So we've got our first step down, that W is a subset of V. Second, so that's the first step on here. Second, is W closed? Well, if I take two arbitrary polynomials of degree 2, so ax squared plus bx plus c, and I add on a second polynomial, ax squared plus bx plus c, and I add these two together, I get a plus a x squared plus b x plus c. And this is a polynomial of degree less than or equal to 2. So we have that this subset is closed under vector addition. Let's check that last property. Let's take an arbitrary polynomial of degree 2 or less, because some of these coefficients could be 0, so that's why I say 2 or less. And if we multiply this by any scalar, we get ac x squared plus bcx plus cc, and this is again a polynomial of degree less than or equal to 2. So this says that W is a subspace of the set of all polynomials. So that means, in particular, it is also a vector space. So rather than checking all 10 axioms, we just had to check these three steps. First, that it's a subset, and that's usually the most straightforward part, and then the two closure axioms. We can test these three, and that's it. We don't need to bother with the other with all 10 of those axioms. Let's look at an example where this fails. So let's take almost the same exact example. Let's take W to be the set of polynomials of degree exactly 2. So first up, is W a subset of the set of polynomials? And yes, it is. Every polynomial of degree 2 is a polynomial, so that checks out. So if we take two polynomials of degree 2 and we add them together, do we get another polynomial of degree 2? This is not necessarily the case. We could have some cancellation in here. Let's in particular say that we have 1 plus x squared, and we add on to that 2 minus x squared. We add those two polynomials of degree 2, and we get this number. This is a polynomial of degree 0. So this is not back in W again. So that says W is not closed under vector addition. So that means that W is not a subspace of the set of polynomials. And in particular, it's not even a vector space. Right? If it fails either of these two axioms, if it's not closed under addition or if it's not closed under scalar multiplication, it's not even a vector space at all. So that was an example of one that failed the closure under addition axiom. Let's look at one where we have the subset fail the closure under scalar multiplication. Let's say that we've got this vector space, or this set I should say. This is vectors in the plane, so this is vectors in R2. So it's already a subset of R2, so we've got that first property sort of done. So that x and y are greater than or equal to 0. So we're going to look at basically the first quadrant. So first up, W is a subset of R2. If I take, this is the restriction of all the points in R2 that satisfy some other constraint. So this is a subset. If we look at closure under addition, if I take a point x, y, and another point st, where these are both in W, that means they're all non-negative, and if I add these together, I get some point x plus s, y plus t. Now if x and y were both non-negative, I add them together, this is non-negative. If both y and t were non-negative, then y plus t is non-negative. So this is again in W. So I know that this subset is closed under addition. If we look at the scalar multiplication, however, take any point in this W. Let's say 1, 1. We should be able to multiply this by any scalar and land back in W. Well, let's multiply this by the scalar negative 1. I multiply this through, we get the point negative 1, negative 1. And this is not in W because the components are not non-negative. So this is not in W. So that means W is not a vector space. And in particular, it's not a subspace of R2. So this gives us a pretty quick way to test whether or not something is a vector space. So with that in mind, we have one more theorem. This we're going to prove in the case of Rn. But you can see how this would extend to other vector spaces. It uses a concept we haven't developed yet, but we'll get to that. And this is the quick test. So this is 4 vectors in Rn. So let's say that W is a subset of Rn, and it is defined in such a way that W is the set of all points x1 up to xn in Rn, such that L of x1 through xn equals 0, where L is linear. If that happens, then W is a subspace. So we've got sort of the flip side of this. If we wind up with this relation right here, where this is anything other than 0, then it's not a subspace. So if W is the set of all vectors in Rn, so that L of x1 through xn is anything other than 0, is some constant that's not 0, then W is not a vector space, and in particular it's not a subspace. So we've seen the idea of linear functions before, but we haven't really given a precise definition. So here we say that L of x and y is linear if L of x and y equals some constant multiple of x plus a constant multiple of y. So think of this like solving a linear equation. We're only allowed to have each of the variables to the first power, and there is no constant term in here. It's ax plus by. If you plug 0, 0 into this function, the value has to be 0 in order for this to be linear. Let's look at an example of where this might fail and where this might pass. So first, an example. Let's say W is the set of all vectors in R3 such that x plus 2y minus 3z equals 0. Well, this right here is our linear function, L of xyz equals 1x plus 2y minus 3z. That is a linear function, and it's equal to 0. So W is a subspace. Okay, let's look at an example where this might fail. Let's look at a non-example. Suppose W is the set of all points x, y, z in R3 so that x plus 2y minus 3z equals 4. Again, this is our linear function. L of x, y, z is 1x plus 2y minus 3z. However, this linear function applied to here gives us a value that's not 0. This is not 0, so W is not a vector space. And in particular, it's not a subspace of R3. Now we've seen this theorem, let's go and let's actually prove this, because the proof is actually kind of illuminating, especially once we look at vector spaces that are not Rn anymore. So here's our theorem that says if W is a vector in Rn, so that this linear function equals 0, this is a vector space. Let's go and prove this theorem. Now we already have. Let me actually just write this out. Let W equal the set of x1 through xn in Rn, so that L of x1 up through xn equals 0. Okay, that's the statement of the theorem, is that W is the set of all vectors in Rn, so that a linear function applied to those equals 0. I want to show that this is a subspace. So the goal, W is a subspace of Rn. Now remember, the previous theorem we had was the subspace test. So we'll just apply these 3 steps here. So first, W is a subset of Rn. It was defined in such a way so that it was vectors in Rn that satisfied an additional constraint. So we have that W is a subset. Let's look at the 2 closure axioms. So let's say that let's take some vector x1 through xn and a second vector y1 through yn. Let's let these both be in W. So what does this mean? Well, this says that L of x1 through xn equals 0, and L of x1 or of y1 through yn is also 0. Well, what does this linear function here mean? This says that if we think of the linear function as a bunch of coefficients, so this says that a1 x1 plus up through an xn equals 0. And our second equation says that a1 y1 plus an yn equals 0. If we take these 2 equations and add them together, we get a1 times x1 plus y1 plus the next coefficient we have in here is a2 times x2 plus y2, and so on all the way down to the last term, which is an xn plus yn equals 0. So what does this say? Well, this right here is the definition of L of the vector x plus the vector y. So this says that if we take 2 points in W, That means that L of x equals 0 and L of y equals 0. We've gone through a little bit of algebra here to show that L of x plus y is 0. That means the sum is also in W. So we've shown that the closure under addition holds. Let's look at the second closure axiom, the second closure property. So what we'll do here is let's suppose that x, which will give as components x1 through xn, is in W, and we'll take this scalar that's a real number. We want to know, is c times x back in W? Right. Is W closed under scalar multiplication? Well, since x is in W, that means if I apply L to x, we've got to get 0. Well, this means that a1 x1 plus a2 x2 plus and so on up to an xn is 0. Now if we multiply both sides of this equation by c, we get that a1 cx1 plus a2 cx2 and so on up to an cxn equals 0. And this, on the left-hand side, this is the definition of L of cx1, cx2,